So I'll try to write big. I know that my phone is a little far away. So we have this graph that we've been talking about, the reaction coordinate. And so what's going on in that one is that we have these reactants. Let's say this is endothermic. So we have this huge jump in energy, and then here's our products. And so what this graph is telling us is that we need a lot of energy to make this reaction happen. And so let's say we don't have enough energy, but we have a catalyst. And so since the catalyst reduces how much energy you need, because what the catalyst basically does is it grabs one molecule, it grabs the other molecule, and it brings them together. And so it makes the reaction happen faster by finding the molecules that need to be together instead of them randomly coming together as they would in a beaker by themselves. And so if you have a catalyst, that's going to lower your activation energy, this part right here. And so if we added a catalyst, we would get the same product, but we wouldn't need as much energy. And so instead of having to go all the way up here, we can stop like right there. We don't need as much energy to get to our product. So the other one that was in the videos, that one's called a Boltzmann curve. Well, do we have any other questions about the catalyst and the reaction coordinate before I move on? So let's see, that's there. We add the catalyst. So this one with the catalyst has a lower EA, or a lower activation energy. Let's see, I can bring this closer so maybe we can see it better. So without the catalyst, we need all this energy going up. And with the catalyst, it makes it so that we don't have as much energy because it brings those particles together instead of randomly, more of an organized fashion. Does that kind of make sense so far? So the other kind of graph that we talked about in the other video, this one's called a Boltzmann curve. And so what that one shows, it looks like this. It'll go up and then it'll kind of taper off. The catalyst does make the reaction easier. And so it's like when we saw the peroxide with the yeast, normally the peroxide would just kind of slowly produce oxygen gas. And then we add the yeast, which has an enzyme which rips the peroxide apart. And so we get that gas faster. So I guess faster would be a better word than easier. It is easier, it's also faster. So for our Boltzmann curve, the height of the line really isn't important. What's important is this area under the curve. And what's even more important is when we have a line right here, and that line's usually going to be labeled EA, or activation energy. What's important is when our molecules hit this activation energy, all of this is how many molecules we have that'll react. And so this right here is the important part of the graph. Everything else really isn't that important. And so I'll bring our camera closer so that we can see that a little better. So all of the area important can stay. But this right here is the most important area. So the height of the graph doesn't matter. What's important is this area, because this shows us how many particles have enough energy to react. And so the more particles that you have that have energy to react, the more reactions you're going to have. So if we lower the temperature, we're going to have a lower probability of seeing a reaction. The area has to stay the same because we can't change the number of particles that are there. But if we have fewer particles with activation energy, that means that this area is going to be smaller. So since this area is smaller, that means this graph will be taller, just to account for the area difference. So even though this graph is taller, it's a lower temperature of a line. If we took the data, this would be a higher temperature and this would be a lower because of this area down here. And so that's how the temperature changes on this graph. The height's not important, the area is important. So if you see one with a lot of area, that's going to be your higher temperature. And in general, your one with the higher area is going to be the shorter peak. Again, to account for that area. So again, I'll bring this closer so it's a little easier to see. This taller peak, if we follow it down, there's a smaller area of particles that have enough energy to react. So this orange line, or this very faint line, is our higher temperature because this area is smaller than the black one. Any questions so far? So if we go back to our idea of a catalyst, we said that a catalyst lowers this activation energy. So if the activation energy is here, this way is increasing. So lower will bring our activation energy to the left. So when we add this catalyst, we now have a lot more area of particles that can react. Because instead of these particles having to have enough energy to collide, now they have something that's bringing them together or ripping them apart. So the energy they have isn't as important because they have something to help them. So we said the catalyst lowers activation energy, so brings it closer to the left. And when we do that, we have more energy under these curves. So see, now our lower temperature can react more. We have more particles at low temperature that can react. And our particles at high temperature have more particles that have enough energy to react. So the area under the curve is what's going to tell you which temperature is higher or not. The placement of the EA, of the activation energy, is going to tell you if there's a catalyst or not. I guess I can write T high and T low on there also to make that a little more obvious. I'll get rid of this because this area itself isn't important. The idea of the area is important, but what's on the other side of this activation energy is what we're going to be judging whether or not there's reactions. So we talked about catalyst, we talked about temperature, now we'll talk about concentration. So I'll remind us one more time that the catalyst makes the molecules have a good orientation for reacting. And the temperature, when you up the temperature, you're giving the particles more energy to react. And so the catalyst improves collision efficiency, or ripping them apart. And the temperature makes sure they have enough energy so when they collide, there's a reaction. It's kind of like if someone bumps into you. If they just kind of lightly bump into you, that's no big deal. But if they come and shove you like down the hall, that's going to be a big deal and you're going to get a reaction. Same idea with the molecules. So when you have a low concentration of something, that means that you don't have a lot of whatever it is you're looking at. So let's say we're looking at HCl, hydrochloric acid. If there's a low concentration, that means that there's a lot of water molecules in the middle. So there's more water than there is, in this case, HCl. And we'll write that as H2O, so it's more clear. Versus the high concentration, we have more HCl molecules than we do water. And so since we have more particles of not water, this one you're going to see a stronger reaction. Like in the video that we saw with the cups that turn purple, if you mix a starch with iodine, it's going to turn black. So if you had a potato and you blended it up, you'd see the same thing. And so when you have more cornstarch, like we saw in cup 1, you have more molecules of cornstarch to react with the iodine. Versus in the low concentration, the iodine has to fight through all the water to find what was our starch molecule over there. So our low concentration, there's more water versus particles of whatever it is, cornstarch, hydrochloric acid, whatever you're working with. Versus the high concentration, there's more particles, starch, hydrochloric acid, whatever, than there is water. So there's more particles to have a reaction with. So that's why you have a higher probability of the reaction. Bravo. Do we have any questions so far? Are there any questions on any of the assignments that you wanted me to go over that seemed confusing? Or did we want another at-home science experiment? Okay. This one? Oh, I didn't share my screen. That might help. So on this one, all right, I'll go over this question and then we'll go over an at-home experiment. There it is. Alrighty, so over here, this one has fewer particles than the one on the right does. And so this one on the right has a higher concentration. And since there's more particles in this box, you're going to get a faster reaction, because think about if you have a lot of people in a room, more of them are going to run into each other. Versus if you have a little bit of people that run into in a room, there's not going to be as many collisions. If you don't have as many collisions, you're not going to see as many reactions. So a higher concentration is going to react the fastest. So this right box would be true for both. Kind of both. You need a collision for a reaction to happen. And in addition to the collision, that collision has to have enough energy and it has to be in the right orientation. Like if you have two fighters and someone hits them in the leg versus hits them in the gut, you're going to get a reaction more if you hit them in the gut because that's the sensitive area. The way molecules are shaped, they're only going to come together certain ways and react. So if they collide in the wrong way, there's not going to be a reaction. Have y'all done the vinegar in the egg? Did y'all do that with Miss Garcia last year? You stick an egg in vinegar for a couple of days, it'll turn to rubber. The same thing happens with a chicken bone. You can turn a chicken bone with rubber by soaking it in vinegar. And that's because the acid breaks down the calcium that's in the egg and the bone. So when you do it, the bone's all rubbery and you can kind of bend it. Have y'all done the Mentos and the Diet Coke? Infamous. If you do it, I recommend you do it outside. And take the Mentos, take your bottle of Diet Coke, and you drop the Mentos gums in there, and the whole thing goes spewing out bubbles and foam. But it has to be Mentos and it has to be Diet Coke. And it works better in a bottle. So the deal with the Coke is probably like if you've seen someone drop like raisins or grapes or something in Coke, all that carbonation starts to grab on to whatever you stuck in it. And so it kind of looks like it's foaming and then it rises to the top.